In this video, we're going to look at discontinuities. And there are four types of discontinuities we're going to deal with. So the first type is removable discontinuity, which is basically like a hole in the graph. We call it removable, so it is removable. I think I'm going to spell removable. There should be an E in here, I think, because we can fill the hole. And what I mean by that is this. So if we have a function and we're just missing this one point, I can fill in this hole with one point and leave the rest of the curve unchanged, and now it's continuous. Now I can have a function like this where there's a hole right there and it's undefined. I can also give it a defined value. Those are both removable discontinuities, where I could just fill in this hole, and one of the later things in this video is going to be how to fill in that hole. A jump discontinuity is kind of as seems, where the function jumps. And if we talk about limits, which we'll eventually get into continuities, the left-hand limit and the right-hand limit are different real numbers. So, for instance, if I have the step function, the floor function, this has many jump discontinuities, where at 1 it jumps up, at 2 it jumps up, at 3 it jumps up, and so forth and so on. Okay, so and I guess let me get rid of this over here. So, well, I'll give another example. So an example of a removable while we're at it is something as simple as x over x. That's going to be the horizontal line at 1, except for x is 0 and it's undefined. Okay? Infinite discontinuities is basically where some of the graph goes to infinity. And I can have it going to different infinities, like in this case, sorry, I'm going to do this way. 1 over x. Or I can have it going to the same infinity, as in 1 over x squared. Both cases, it has this discontinuity at x equals 0. It doesn't matter that in this case they're pointing towards the same infinity. There's still going to be some break in the real values of this graph at 0. Then the final one is an oscillating. And in this case, so if we're trying to look at this as limits, these don't have limits. This one doesn't have a limit because they're pointing towards different things. This has a limit, but the limit's not a real number. These don't have limits at the jumps. This has a limit, but there's this missing point where the limit is. Oscillating don't have a limit. And one example of that is sine of 1 over x, which is going to look something like this, where it oscillates faster and faster and faster, and it's actually going to be undefined at 0, and then it picks up again, oscillating quickly, 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 and then settles down. Now that might be a little bit off, but that's the basic idea. So these are our four types of discontinuities. A common question might be to find and classify all discontinuities of a function. Now, if I have a rational function and I don't have a graph of it, I can just do some work on this and see what happens. And for polynomials, they're continuous everywhere. For rational functions, the only thing that can go wrong is if this denominator is equal to 0. So only discontinuities at x squared minus 1 equals 0. But that doesn't tell me what type, and here's what I'm going to do. I'm going to reduce this down. So f of x is equal to x squared plus x over x squared minus 1. Factor the numerator, factor the denominator. And I'll get x times x plus 1 over x minus 1 times x plus 1. And here, I'm going to cancel these out. And so f of x will equal x over x minus 1 almost everywhere. It will not be equal here when x is negative 1. So x cannot equal negative 1 because this is undefined at negative 1. This must also be undefined at negative 1. And what this means is the following. So let me write this out. If the 0, let me say the factor in the denominator cancels completely, as in the x plus 1, then we have a removable discontinuity. So this means that we have a removable discontinuity at x equals negative 1. If the factor does not cancel completely, then we have an infinite discontinuity. And in this case, the x minus 1 did not cancel completely, so we have an infinite discontinuity at x equals positive 1, the 0 from this. And notice how I say cancel completely. If we had, so I'll give a little example, if I had something like this, x cubed over x to the 4th, a bunch of these cancel, but I'm still left with one. That would still leave me with an infinite discontinuity at 0, even though a bunch of them do cancel. The idea is, as I divide some number by an exceedingly small number, that division will give me a very large number. It goes off to infinity. And we can see on the graph right here that yes, we do in fact have a removable discontinuity, a hole here when x is negative 1, and an infinite discontinuity here when x equals positive 1. So what about extending a function? Extending a function basically means filling in the hole. And the purpose for this is to make it continuous at a given point, some given point, and you'll be given the point unless there's only one discontinuity, in which case that's the point you would have to extend it at. Okay, so a couple of things. First off, you can only extend at removable discontinuities. And that should make sense let me flip back here. I could try to fill in this hole, everything else is good. I could try to fill in this hole, everything else is good. There's no way to fill in this gap without making this not a function with a vertical line. There's no way to fill in this point that they're approaching because infinity is not a real number. 0, infinity is not a point on the Cartesian plane. There's nothing to fill in here. It's going to be somewhere between -1 and 1, but we don't know and can't know. And even if we tried to know, there's as good of an argument for any of the other points, so I can't fill this in. So only for removable discontinuities, and there are 2 forms that I can take it in. So if I have a rational function, I have an option to just cancel I'll say the offending factor, and bam, there's your answer. That only works for rational functions. For all functions we are extending, we can make a piecewise function. So the idea is, I'm going to put a little e down here for the extended function. And I'll say, I'll take the actual function for all x not equal to whatever that critical value is, and I'll take some other value at that critical value. I'll fill in that hole, whatever this critical value is. That can sometimes take some doing to get. So let's see 2 examples. The first one is the same function we were dealing with earlier, and I'll do this by hand. So we start off with f of x is equal to x squared plus x over x squared minus 1, factor the numerator, factor the denominator, x times x plus 1, over x minus 1, x plus 1. As we saw before, these cancel. However, when we cancel them, I will get x over x minus 1, but to make these actually equal, I need to sort of say that x cannot equal -1. In this one, before I canceled, I can't put -1 in because that would be 0 over 0, which is undefined. If I tried to put -1 in just this part, I would get -1 over -2, which we'll get back to shortly. And I shouldn't have it defined. F of x is not defined at -1, so I have to specify that. Now, a couple of options. If x equals -1 is the sort of thing I want to make this continuous over, one option is to just say that the extended function is just going to be equal to x over x minus 1, because these functions are equal everywhere except for at -1, and this function is continuous through -1. So that's one way to write it, and it works great for rational functions that do reduce. Or I could also write like this. I could say that it is equal to the original function, x squared plus x over x squared minus 1, so long as x is not equal to -1. And now I need to figure out what does it equal at -1, or what should it, where's this hole? And what I'm going to do for that is say, okay, well, I know it's going to be this value that I want to fill in at -1, so I'll just do -1 over -1 minus 1. I'll see what that value is, and that's going to be -1 over -2, which is 1/2, and so I could put the 1/2 in here, and that will fill in the hole as well. Both are acceptable. This is going to work for things that don't just reduce. And let's see graphically. So you see this right here, and we have this hole right here at -1, 1/2, and if we filled that in, we'd have a continuous function. All right, last example. This one I can't use that simpler way to do it because I can't reduce this down. So I actually need to figure out what this limit is. I need to figure out where this hole is. So the hole is of course going to be where x equals 0. That's what we're trying to fill in because I can't divide by 0. And y would equal what? Well, let's look at the graph of this. So I get rid of the f function. and then we turn on the g function. Okay, so here's what that looks like, and I have this hole up here at 7/2, 3.5. So this shouldn't be too surprising because I see this 7x and this 2x, and that is why that is there. So the extended function here is going to be sine of 7x divided by 2x for all x not equal to 0, and just 7/2 at x equals 0. Alright, I hope that helped out. Please comment below if you do have any questions.